This is problem 32 from the photon. You should turn there in your textbook. Problem 32, we have a 0.03 nanometer photon colliding with an electron at rest. After the collision, the photon is detected at 40 degrees relative to its initial direction of travel. We have a picture of the situation here, and we have the equation from page 7 for Compton scattering, which we are going to use, and that's here. From the appendix, you should see that Hc is equal to 1240 electron volt nanometers, and mc squared, this is for the electron, is 511 kilo electron volts. We want to find E prime, and remember that E prime is equal to Hc over lambda prime. So you can find lambda prime from our equation for Compton scattering. So lambda prime is the wavelength after the collision, and we can bring lambda over to the other side and say this is equal to lambda plus Hc over mc squared. Hc is 1240 electron volt nanometers, that's a constant, divided by mc squared, that's for the electron, and this is 511 kilo electron volts times 1 minus cosine theta, that's the angle that the photon goes off at after the collision. That's 40 degrees, and this lambda is 0.03 nanometers. And that gives us 0.03 nanometers plus 1240 electron volt nanometers divided by 511 kilo electron volts gives us 0.00243 nanometers times 1 minus cosine of 40 degrees is 0.234. And that gives us, for lambda prime, 0.030569 nanometers. And finally, to find the energy, we have E prime is equal to Hc, which is 1240 electron volt nanometers, divided by the wavelength of the scattered photon, which is 0.030569 nanometers, which gives us the energy in electron volts. That is 40.564 kilo electron volts. And that is the answer for part A. For part B, we are asked to find the kinetic energy of the scattered electron. Initially, the electron is at rest, has kinetic energy after the collision. If we go back to page 6 in the textbook, for this situation, we did conservation of energy, and we wrote out the initial energy of the photon plus the rest energy of the electron, because it was initially at rest, is equal to the final energy of the photon plus the energy of the electron. But the energy of the electron is its rest energy, mc squared, plus its kinetic energy. So we can write that conservation of energy as E plus mc squared is equal to E prime plus mc squared plus the kinetic energy for the electron after the collision. But the electron has rest energy before and afterwards, and it's the same before as it is afterwards. So we have E is equal to E prime plus the kinetic energy. So the difference in the energy of the electron before and afterwards is the kinetic energy, or the difference of the energy of the photon before and afterwards is equal to the kinetic energy of the electron. This is why the wavelength of the photon changed. So before, the wavelength was 0.03, afterwards it's slightly higher, which is 0.0300569, And if the wavelength is larger, the energy is smaller. So the wavelength increased, the photon lost energy, it gave some of that energy to the electron. We want to find what this kinetic energy is. And we already have E prime. So if we had calculated E to begin with, we could have just put it in here, but we didn't do that. So we have E is equal to hc over lambda. So this is 1240 electron volt nanometers divided by 0.03 nanometers, and the E prime is just 40.564 kilo electron volts. So for this, the initial energy of the photon, we get 41.333 kilo electron volts minus 40.564 kilo electron volts, and that is equal to 0.769 kilo electron volts, but let's write that as 769 electron volts. So that is the kinetic energy of the electron after the collision. We also want to find the angle of the scattered electron. Our equation for Compton scattering only has variables from the two photons, so if we want the angle for the electron, we have to go back to our momentum equation. And this is in the y direction. We know that the initial momentum in the y direction is 0, so I can say after the collision, the energy of the photon times sine theta is equal to the momentum of the electron times sine phi. I'm looking for the angle. I want to find phi. And I know E prime, I know theta. I'm looking for phi, but I don't know the momentum of the electron. But I can find the momentum of the electron by using E for the electron squared is equal to mc squared squared plus PEC squared. And I have mc squared is 511 kilo electron volts. I'm looking for PEC squared. I need the energy of the electron. This is after the collision. And after the collision, the energy is the kinetic energy plus mc squared. So I have my kinetic energy is 769 electron volts, and the rest energy is 511. The 769 electron volts is 0.769 kilo electron volts, and the rest energy is 511 kilo electron volts. So this would be 511.769 kilo electron volts. So that's the total energy of the electron after the collision, 0.769 kilo electron volts squared. So the momentum would be the square root of 511.769 squared minus 511 squared, and that gives us 28 kilo electron volts for the momentum of the electron after the collision. Now we can go back to the equation that we have here, and let's say phi is equal to the inverse sine of E prime times sine theta divided by PEC, and that is the inverse sine of E prime. E prime is 40.564 kilo electron volts times sine theta theta is 40 degrees, divided by PEC, which I just found to be 28 kiloelectron volts. The kiloelectron volts cancels out, and you get phi is equal to the inverse sine of 0.932, which is 68.8 degrees. And that is the answer for part C. So that concludes problem 32.